this is PrachiGupta. Welcome to my next collab video. Here we are going to see why deep learning works, geometric intuitions. So let's see, understanding neural networks through space folding. So in this notebook will give you a deep geometric understanding of why neural network works. We visualize how neural network learn complex patterns by folding and bending space. An insight that makes deep learning suddenly makes sense. It's based on brilliant well labs video. First, the big question is, why do deep network work so much better with wide networks? Well, the answer is the hands-on visualization. So, what we will learn in our journey, the challenge, the complex border that's hard to classify, linear limits, why neurons can only draw straight lines, the folding insights, why ReLU bends and folds space, the key insight, wide versus deep, why 5 layers cross 32 neuron beats 1000 neurons plus 1 layer, and proof that watch deep networks succeed with shallow one fails. We'll see the visual overview, the core insights, why shallow networks and how deep network works and why it struggles and why it succeeds. We'll see that. So first let's start with the setup. We'll import everything what we will need, and then we will just run this. So once the execution is completed, it will say the setup is completed, and it's installing the required files. So it's okay, let it install, we will move forward. Yeah, it is done. Okay, so the part one is universal approximation theorem. So there is a beautiful theorem in the mathematics, the universal approximation theorem. A neural network with just one hidden layer can approximate any continuous functions given enough neurons. So this sounds amazing. It means that theoretically we never need deep networks. A single wide layer should be enough. But here is the catch. The theorem says a solution exists. It does not say you can find it easily. It does not say it will be efficient. So, in practice, many billions of neurons training might never converge, the gradient descent gets stuck. So, let's see it in action. So, we have defined a universal theorem, approximation theorem function to show how wide network can approximate a function but may need many neurons. So, here we are getting a target function with a complex Vigi curve. We are setting a array of from range -3 to 3 with 1000 space points, and with a target point as sine of x plus sine cosine into sine. So this is what we are setting as the target. Now we will simulate what n neurons could approximate. So we will create a zeros like approximate array, and then we will the random neuron we will do ReLU, that is wx plus b with random weights. So we will define w and b, and then we will do the ReLU out with maximize, and then we will store the y approx value. So we'll scale to match the target roughly. So we'll scale the y approx to match the target roughly, and then we will plot it, and we will see the uh, plot, and we will see how it actually works. I'll just run it. So this is how with one neuron we can see the errors, with two neurons how much error gets, with five neurons we can see the errors, with 10 neurons we can see the errors, with 50 neurons, and with 200 neurons. So the lesser neurons we had, the lesser the error we had. So yes, we can use we can approximate any function, but the complex patterns we might need millions of neuron. Is there a better way? Yes, let's go deep. So the challenge is a complex border, the Belgium Netherlands border problem. To really understand why depth matter, we need a challenging classification problem. The video uses the border between Belgium and the Netherlands, a famously complex wiggly line that hard to separate. Let's create our own version of this challenge. So the classification challenge is we want to separate the blue points and the red points. The border between them is very wiggy. So can a neural network learn this border? So let's define a function, create complex border dataset where we have the samples and the noise. This dataset we are creating with a complex wiggly decision boundary. This mimics the Belgium Netherlands border challenge from the video, and then we are defining number of points to generate, and then we have defined the noise also, and we will return x the points and the y the labels. So here we are generating random points in a square and then creating a complex wiggy boundary here. So this is the boundary that we are creating. Then we will add some noise to make it more harder, and then we will classify based on the position relative to the boundary, and then we will return x and y. Then we are defining plot dataset to visualize the dataset with its true boundary. So we are doing the plotting part here, plot true boundaries, and then once that is done, we will show the boundary and return x. Now we will create and visualize our data set. So this is our x train and y train. We are creating the data sets and then we are plotting it, and then we will just run it. So let's see. So this is our data set and this is the boundary that we have drawn. So the challenge, 2000 data points, two classes separated by a very wiggy boundary, and can a neural network learn to separate them? Let's find out. So what is a single neuron can do? Linear decision boundaries. Before understanding the deep networks, let's see what a single neuron can do. A single neuron computes z is equals to w1 x1 plus w2 x2 plus b, where w is the weight, x is the input, and b is the bias. So this classifies based on whether z is greater than 0 or z is less than 0. So what one neuron sees is x2, class 1, class 0, x2, and this is a straight line. One neuron equals to one straight line. Can't handle a wiggy boundary as we have already discussed. So here we are defining a visualized linear classifier. Show that a single neuron can only create a linear boundary. This is why we are creating this function. So we have defined this plot function, and then we create a mesh for the decision boundary visualization. We have created a mesh grid here. We are defining this linear classifiers here, horizontal line, diagonal line, detailed line, all these classifiers we have defined. And then we are computing the decision boundaries here. We are plotting the decision reasons, we are plotting the data, and then we are calculating the accuracy here. Once we have calculated it, we will plot it, and then we will call the visualize linear classifier. Now let's run this and see how it actually works. So we can see horizontal line, it it gives the accuracy of 86%. Vertical line gives the accuracy of 69%. We can still see the red dots here, and the tilted line also doesn't not is not able to make separate it properly because the boundary is very wiggy and not straight. So this is the problem. A single neuron can only draw a straight line, and that's why we can't uh, use it where we have the wiggy boundaries and it won't be fit. So we need something more powerful, and there the magic of activation function comes. How ReLU folds this space. This is the key insight of the video. So this is the key inside of the value. The ReLU, that is rectified linear unit activation function, does something magical. So it gives max of 0 comma x. Either it if x is greater than 0, then it will return x, otherwise it will return 0. It looks simple, but it has a profound effect to fold its space. So negative inputs, it will squash the flat to 0, and if it's positive, then it will be unchanged linear. This creates fold or bends in the space. Let's see how. So we are defining a visualize ReLU folding. Here we will plot it, and then we will the ReLU function itself we are defining here, and then we will plot it. We will do the 1D folding visualization, and then we will set up the original space, and then we will show the folding with arrows here, with gray arrows, and then we will do a 2D space folding. Again we will create a 2D match grid for it, and once that is done, we'll use the single neurons and show the fold. And then again we will use multiple neurons with multiple folds. Here are three neurons with different orientation, and then we will show the fold lines here. So once this is done, we will call the visualize function, and we will see how it gives the output. So if you see, this is the ReLU's activation function um, for just a second. So the for this is ReLU's activation function for negative and zeros. This is the multiple neuron fold, and this is the one neuron that creates the fold. So key inside each ReLU neuron creates one fold in input space. More neurons equals to more folds and more complex boundaries. So one neuron you can see one single shade. But if there are more neuron, multiple folds, and you can see different colors and different filters for the shades. So, but there is something more powerful, the power of depth, exponential reasons, wide versus deep, the key comparison. Here is where the things get excited. Adding neurons in the width versus depth has very different effects. So how it is different, wide versus deep in the maths. So wide add neurons in one layer. Each neuron adds one fold, and n neurons equals to n folds, roughly n plus 1 regions. But deep adds the layer. So in wide we are adding the neurons, while we increase the depth we are increasing the layers. So wide is equals to 100 neurons into one layer, whereas deep equals to 10 neurons and 5 layers. So let's see how we can compare the depth versus width. We will define a visualize depth versus width function, and then we will plot it. We will create a grid, and then we will do row 1 as a wide network, increasing the neurons in one layer, and simulate a wide network with n neurons here. And then we will plot it, we will count the region approximates, and then we will set the labels accordingly. In the second row we are doing the deep networks, that is increasing the layer. So we will increasing the layer. We will simulate a deep network within n layers. So number of neuron per layer we have defined 4. We will start with the input grid, and then we will for every layer we will plot it, and then we will show the final output. And using the plot we are going to display the output. Let's see how it actually looks like. So you can see depth creates more complex decision boundaries. So these are 20 neurons with one layer, and this is wide, basically two neurons and one layer. This is 5 neurons and one layer, and this is 20 neurons and one layer. While as instead of 2 neurons in one layer, if we do 4 neurons in one layer, it will look something like this. If we do 4 neurons in 3 layers, we will be able to define more precision boundary, and this is how we are doing it. So wide is basically adding neurons to create more parallel folds, while deep is adding layers to create hierarchical folds, and deep network with fewer total number neuron create more complex regions. So the proof of training real networks. Let's put it to the test. Now this is the moment of truth. We will train two neural networks on our complex border. Network A is shallow and wide, one hidden layer, 1000 neurons and total 1000 parameters, versus network B where deep and narrow. So we will have 5 hidden layers, 32 neurons, that is total 160 neurons. Which one will be for which one the VG border will be better? One with the 1000 parameter or one with the 160 parameter? Let's find out. So we will create two classes. One is the shallow network class and one is the deep network class. Again we will do the forward and then the we will define the forward here in the deep network as well. And then we have this function called count parameters. We have this function for training the network, and for each epoch we will do the forward pass, backward pass, and then track the matrices. And then we will plot the decision boundary here, and to plot the decision boundary we will create the mesh, we will get the predictions, and then we will plot, we will set up the true boundary, and then we will print the output. So let's see, we will call the shallow network with hidden size 1000, whereas we will call the deep network with hidden size is 32 and number of layers is equals to 5. So let's see for which the wiggle boundary comes better. Neural network class defined network comparisons. uh, this neuron shows 4001 parameter, whereas the deep shows 4353 parameters. So this is what we can see. Now training a shallow network, let's train the wide shallow network and so see how does it do it. So we'll run it and we'll see how shallow network works. So it is doing epochs, um, and we can see the final accuracy is 97%. Now let's train the deep network and see how it will work. It is 97%. Now let's see the deep network. We can see the final accuracy is 98%, which is more than the shallow network. Deep network has more accuracy. So this is, we have the final comparison, and we will visualize each network had learned. So we will plot the decision boundaries of both shallow and the deep model, and then we will see how the difference look in the visualized form. So if you see, this is the boundary created by the shallow one, and this is the boundary created by the deep neuron. So you can see this point, it is very clearly observed by the deep neurons, but whereas the shallow neurons have left in the accuracy behind. And even the epochs, in the epochs you can see the accuracy comparison and the loss comparison. So that's why the result is like the final accuracy of shallow is less than the final accuracy of the deep. So this is why deep learning works and the geometric intuitions. So these are the key takeaways from the class and visual summary. So thank you so much. We have completed this part. Thank you.